So let's continue with the gapped inductor, right? So the reason we like to use the gapped inductor mainly because of the saturations. For all the magnetic devices, I think saturation is something we need to really concern. You can see that a gapped inductor, this kind of the air gap in here, more look like an additional resistance to the inductor or maybe to a transformer. So in this case, we can use this gap in order to restrict, to limit the amount of the magnetic flux pass through the system. A magnetic circuit like this more look like we got driving force, which is the magnetic driving force is so-called Ni. It's a kind of the so-called MMF. Just remind you, MMF is the driving force. Look like the voltage. But in magnetic circuitry, we don't call it voltage, we call it MMF, the driving force called Ni. Mi represent for the electromotive force, really famous name. So we do have this driving force applied for magnetic core, and then together through the magnetic core, then through the air gap. So that's totally two components. So this component, obviously you can see that are connected in series. So that's why both of them will share amount of the input force, just like share the voltage. So the basic equation for the reluctance, which is the opposition term, we call reluctance. Then you can imagine it more look like resistance in a circuitry. So that reluctance are given by L, the length for the path, divided by the mu, which permeability and the area. So that's a really physical equation based on the dimension, based on physical parameter, based on the geometry. And of course, based on the permeability material inside. So this equation, you can see that very similar to the resistance equation. And then we can therefore list out the two resistance and then putting here look like an equivalent circuitry. That circuitry is really much similar to the voltage equation, right? Circuitry. And then from there, we can therefore work out the flux. The flux, we call it flow component. Then which you can imagine that more look like a current. So this thing, when we divide the driving force, like the driving voltage, divided by the resistance, which now become reluctant, you can get the driving current, the current here, which is now the flux. Once you obtain the flux here, then the flux is divided by the cross-sectional area, become the density. B is called the magnetic flux density. We usually try to use the B density because all material, they respond to the density more. Just like current density, or in here with the magnetic flux density. All the material, they got some restriction. They cannot have too high magnetic flux density, otherwise saturated. So that's why we tend to use this method to firstly measure about to see what kind of magnetic flux density would be suitable. And then we may also adjust the air gap to control it. Okay. So now then we can have density to calculate the magnetic flux density here for the core, for the air gap. And the flow component flux here, I can see here we use core, the flow component for the core, C, or for the gap. Because you can see that this magnetic flux passes through both of them. So this flow component should be equal for both components, for magnetic core and the air gap. It's equal, so we can just, these two are equal anyway. And then for cross-sectional area, so in theory, the area for this core more look like the physical size for the magnetic core. And then for the air gap, this area, how much air area to contain the flux is ambiguous. We're not quite sure. We need to measure, we need to use some special tool to measure it. But usually if the gap is really small, the area enclosed the magnetic flux in the air should be very much close to the magnetic core. So we can assume this two to be equal, then you can see that two air gap will be the same. You see, for power electronic or magnetic design or for machine design, for simple classroom exercise, we usually assume them to be the same, easier for your calculation. But of course, in practical manner and practical design, they are slightly different. They may differ by 10%, 20%, maybe more, depending on the air gap. So this is a typical example. We are using a relay to show the operation. A relay, I think you all use a relay in the past. The relay will be when we are putting the magnetic energy in here, then attract here, then air gap will become 0, right? Before that, we have air gap. So let's see the question. We got 500 number of turns here. We got magnetic core length, which is this length here, without air gap, 360. That means 0.36 meter. And the air gap supposed to 1.5 in here. And then the B field need to actuate the relay, and the typo here, relay will be 0.8 here. So the force require the actuator to produce the attraction to couple them will be 0.8 Tesla. So we need to produce 0.8 in this location. So that's the requirement. We given that the magnetic flux density, H field, the magnetic flux is equal to 510 AH. So that's the given component. So now then we need to calculate what kind of current will be needed, what's the permeability, when the relay is closed, what will be the current needed. Let's do some simple example to see what. Firstly, if you know that from that material, the B field is 0.8 Tesla for the actuation, and during that time, the H field is 510. So using these two components, then we can therefore work out the MMF for the driving force, right? So H field is the magnetic component, and the core length, LC, is the length. So you just simplify 10 multiplied by 0.36 will give you 184 driving force. That's the MMF requirement to drive the coil. The unit here is 184 ampere turn. You see turn actually without any unit. So that's why many researchers, they don't use the T there. They may only use 184 ampere. That is also good enough. You don't need to put T, but you can put T if you like, because T is not unit anyway. And then for air gap, the amount of driving force appear on in the air gap, then we can see that will be the same kind of the B field, yeah? And then we can divide them by the B field is the same anyway for the two core component and the air gap component. The divide by the mu naught will be the H field in the air gap. So just this one divide by that one. So you can see that the H field between the core and the air gap are quite different because they have different permeability. Permeability is control how much H field we can have. So in air gap, because permeability is equal to mu r equal 1, so we have different permeability. And then multiply by 2, because we have 2 air gap here, 1 and 2 air gap. So 2 multiplied by 1.5, then we got the MMF here. So obviously you can see that the driving force, which distribute across two components, one is the magnetic core, one is the air gap, and then magnetic core have a relatively smaller kind of MMF. More the MMF will go to the air gap. So you can imagine quite straightforward by relay them into a electrical circuit. When we have two resistors, smaller resistor, less voltage. When you want to potential divider, right? High resistor, you got more voltage, can be distributed on that. So this is how it look like. And total MMF with summation of these two. So that's the driving force requirement from the coil Ni. So this driving force, we know the driving for MMF equal to N times the current, the basic formula. So there's a number of magnetic formula you need to memorize. And then that's why 2094 divided by 500 turn will become the current requirement. Okay, so that's the current you need to drive the coil to achieve this B field.
Here, there is less resistance. If we think about that, then MMF should be less.
You say when the air gap is the one we control the reluctance or the resistance for the magnetic flux to go through. So the air gap here, firstly, because for relay, there must be air gap here.
Yes.
So that's why your driving force need to provide certain good magnetic flux into core. Because this also need to penetrate through the air. So this gives you a resistance which the relay doesn't like. But air gap must be there because relay must have air gap. Yeah. So that's why you are putting more energy, more current requirement for the relay before closing the air gap. Yeah. So that's why I can see that we're putting 4.19 amp to energize this action. So this 4.19 amp are putting this 2000 something mmF, quite large value. And most of this 2094 actually go to air gap. Yeah. We have to, because we need to contribute the driving force, the MMF, to most air gap. That's the phenomenon for the relay, right?
So, the thing is, because of the air gap, we need more current.
We need more current,
So
more driving force, more input. Driving for MMF is the driving energy, right?
we are designing it for the relay.
Yeah, for the relay. This problem is for the relay. Yeah. So before the actuation happens, we need the driving force, the more current on the coil to drive the relay, to provide MMF, to attract the unit back to the coil side. And then in here, we can quickly calculate permeability for the core. So that means the B, we know that 0.8 is given here, divided by HC, which is also given, then the permeability is equal to 1.57. But that is the permeability, not the relative permeability. You know, the equation for the relative permeability is that we like to usually we document this for all the components. If you buy any magnetic core, design a motor, you need to ask for, I need to buy a magnetic core with a mil R equal to 1,000, 10,500. You need to tell them. We don't tell this. This is too complicated. So that's why we divided by the free space, the mu naught permeability. I think you all know that. So do remember this parameter constant. I think you do. Have you memorized this? Mu naught? I think you all know, right? The mu naught, the free space permeability. I think we all know 4 pi 10 to power minus 7. I think, yeah. Then we get this give us the mu R 1250. So that means the magnetic core have a mu R equal 1250. Not really high permeability, but reasonable for relay. And then now the next part will be if the relay is closed, that means air gap becomes 0. What kind of current? Then we can see the current should be reduced because we don't need that much driving force to appear in the air gap. So under that case, then the air gap MFF will equal to 0 because disappear. So that means then the driving force only need to provide the driving force MMF to the coil with the core. So that is 510 multiplied by length, which is already calculated here, is 184. So we only need 184 mmF for the operation. So the current would quite straightforward, 184 divided by 500 turn becomes 0.36 ampere. So that means you can see that before we actuate them with air gap, we got a lot of current 4 point something amp, but now we got 0.3. So that this example firstly show you the principle of the relay. Also show you how the MMF appear in all that connection, including the core and the air gap. You also see before and after, we need different current to drive the machine. So this, although a very simple machine, a relay, but you see a relay, once you actuate, before actuate, how the current look like. Okay, just a really simple machine, yeah, electrical machine. But from here, we just learn how to understand the parameter. I think you do all learn this parameter, right, in the past. Have you all learned this? This example, really simple. I think you all know in the past. Servo, have you learned this in the past? Yeah, in the high school, probably in the physics, right? Yeah, okay. It's just quick revision, yeah. And the next topic we try to examine about the inductance. I think these chapters are all very simple, have quick revision of what you learned in the past. So, but you have once, but the thing is, even though something simple, but if we revise that, we can think about something. I would like you to, even though they're simple, make use this lesson, think about something you can do, connect this with your research. Yeah. For instance, when you see inductor, oh, I can design inductor in such a way. Can I connect it with my maybe electric vehicle design or maybe solar power design? Put an inductor, what happened? I want you to do something like that. Okay. So now, first linkage is one of the term. Do you know first linkage? I tell a story, right? And we try to recruit some engineer for my researcher. So first linkage is the terminology we teach students in all the undergraduate, year 1, year 2. Everybody knows first linkage. And then this guy, when I try to interview him, supposed to apply for me how to design motor. So the first simple question I like to ask him would be, can you explain to me what's first linkage? He didn't know how to answer, right? Such a basic question. Although the terminology is so basic, inductor, first linkage, magnetic flux density, those simple terminology, you all need to memorize 100% without any hesitation. In case your future employer like to ask you some question when he interview you, to give you some kind of the souvenir first question, if you can't answer, that will be a disaster. Like, what's the meaning of first linkage, right? Just really simple answer, simple question. So you do need to understand what it is. So first linkage means you got a flow component first. This first will link to something, right? Link. If you put one coil, you link to one coil. That's how much MMF electromotive force component contain. When you put more turn, you can link more turn. So actually, first linkage relate to the MMF driving force. You use the number of turn to link more coil. So that's how we call the first linkage. Okay, so that means the first linkage is term lambda equal to n phi. So that's the term you must know, that is to link to the coil. More number of term, you can link more coil to appear to have more MMF driving force. Yeah. So that means the definition for inductance, you also need to know what's the definition of inductance. I think we all learn inductance for 20 years, right? But now if your boss asks you what's the meaning for inductance, basic definition from the basic physics. Then the basic definition is first linkage per unit current. Because you see, when I have many number terms, we link to the coil, we need to see how good the energy storage is. So that's called, to define that one, we say the first linkage per unit current, you can draw that. So that means if high inductance, we don't need to use that much current, can still have a good inductance. So that's the definition, right? So you need to understand physical principle, why we do that. If I ask you about what's the meaning of inductance, oh, this is equal to N squared A over L. That's not a definition. That's only a formulation. Definition is first linkage per unit current. Okay. So now then, in here, although something really simple, but when we revisit them, we can more thinking. My teaching here just to stimulate you have additional thinking, to think more about any problem, any something simple, we can still able to explore the concept further. So that is the first linkage equation. And then from there, we can just using normal substitution to replace all this, become our famous formula here, which is a basic formulation for the inductance, which what we did with the flux equal to density multiplied by area. We'll put into here, and then H equal to relate to the B field by this mu log formula. So we put these two formula into here, and then also the H field equal to Ni, the MMF, divided by the length per unit length is the H field, right? Put all into here and then come back into this really famous formula for inductance. All the inductance formula are really similar to this. So that's resultant of the first linkage. So which you can see that all the inductance are proportional to N squared, proportional area, and inverse proportional to the length for the core, and of course the permeability. And then this formula, you can see that this term, physical parameter, which equal to reluctance, happen to be so. Inductance also equal to the number of turns squared divided by the reluctance. So that is how we get a correlation. So you can see magnetic design are something really highly correlated to each other. Although formula is simple, in the past we learned the formula, but when we revisit them, we can see something more. So that's how we understand the inductance. Okay. Any questions? So here will be another simple example, just to show you about the. So we got our magnetic core here, magnetic circuitry, and then we say, so assume the N is say 400 number of turns, 400 turn in here, pass magnetic circuitry, and then the core length will be 50 centimeter. We do have some small air gap in here, which is 1 mm. And the cross-sectional area A here, cross-sectional area is 15 cm. We assume the air gap, core air gap, and the AG equal to AC, right? Make it simple for calculation. The permeability here is 3,000. The driving current here, 1 amp. Calculate the flux density or the flux component in the air gap. So if we assume the flux only pass through the core and the air gap, so we use to assume the flux density will be the same in here and the same in here anyway. Calculate inductance. So now then, firstly, we start with the reluctance, which will be the length. Again, is the all physical parameter. Yeah, this one. So we can get the reluctance equal to this one, 88. Air gap, right? We got the length for air gap divided by the permeability divided by the area. Then we can get the reluctance for the air gap. So now then we got total opposition term from the reluctance. Driving force Ni 400 term times 1 amp current. Then we can get the through component, which is the magnetic flux. The magnetic flux unit equal to Weber. I think you do need to memorize, right? I think you all know that. So the density, this flux will pass through this area. So that means the flux divided by area be 0.43 Tesla. So that's how we got that. Very straightforward calculation. So after that, then the inductance, then we can using basic formula. We got number of turns squared divided by the reluctance. Now we got two reluctance. One is due to air gap, one is due to magnetic core. Then that will give you this one. Or you can also using the flux linkage divided per unit current. Then also flux linkage per unit current also give the same. They're the same formulation anyway. Okay, so that's how again, I forgot to put down 400 in here, 400 turn, but just so we might N equal to 400. So that's it for this simple problem to show you the operation. Another discussion will show you about toroidal core. The transformer inductor can be many shapes, can be square, can be toroidal ring core. So that's really common transformer geometry. So here will be toroidal core as shown in here. Number of turns will be 250 in here. And then the inner diameter, outer diameter will this 20 and 25. So from 20 and 25, you can be very easy to calculate cross-sectional area here, right? Just inner and outer subtraction divided by 2 and get the diameter here. So air gap length, we assume somewhere we got air gap length in this core is 1 mm. The cross-sectional area for the core, then we can be given to be 15 cm square. Then we can, the relative permeability, μr, you do have a data sheet you can refer to, which is this one. You see, sometimes the μr may not be fixed value, can be from a variable, depend on the manufacturer data. Although in some simple calculation, we assume the μr is fixed. But you can see that from a BH curve like this, they can't be a fixed value. The μr is more look like the slope in here. So initially we got sharper, in here we got less, right? So that's a μr is not constant. So we can therefore, from this ratio, we can get the μr. So anyway, so we ask from the manufacturer data to get the μr later on. So if our product current is 2.5 amp, we need to calculate the flux and the flux density in the air gap, the inductance, and also what's the permeability at 2.5 M. Why we have that statement? Because for different current, the permeability can be different. Because this relate to the H field here, the flux intensity. The flux intensity equal to proportional current, right? Ni, right? Ni. So that's why when we have high current, the field intensity will become higher. So that's how it. So firstly, we calculate the mean rate. This is outer 25, inner will 20. So the mean radius will be this one, the average of these two divided by 2, right? Then we come the mean radius for the metal core. And then the length. So because once we got to mean radius, we can this top that is will be just 2 pi r, right? 2 pi r. We can get that. So that is how we get the H field 442. So now that we get the H field, the thing is the mu r is a fixed parameter. So we can from here 442 somewhere in here, 442 here, then go up here. Then get the B field equal to 1.225. Yeah, that's the way we look up the table. In power electronic machine design, we always using the BH curve for the manufacturer to look up. We don't mu r level can be a fixed value. Okay, when you apply certain current H field, then you can get certain B field. Okay, that's how we get that. So inductance for the coil, then we calculate the cross-sectional area for the system. So 25 minus 20 divided by 2. So that is to say in here, 25 minus 20 would be this sum of this one and sum of this one divided by 2 become this one. Then we divide by 2 square. Let me double check if that's the right area. Pi r square, we tend to get the area for the flow component, right? (25 minus 20). Then we got this one and adding this one. And then this one divided by 2. Then we're having the whole length of this one. Yeah, but that's a radius. We just divide.
20 is inner.
Yeah, I double check. I think that may be divided by 4. Yeah, but anyway, that's the concept. Yeah, once we get this one, then square, then we got this area in here, A. Yeah. So if you get this area here, then later on we got the B field. We have this core B field and multiply by this area. Then we got the magnetic flux. Yeah. So again, the first linkage will be N times 5 will be this one. Times 5 will get this one. And then per unit current, we got 240 mH. So that's the way we can calculate the inductor anyway. So next question, what's the permeability, right? Permeability, again, B over H is the mu. So we got B field divided by the H 442. We have this permeability. So this one is inconvenient. We divide the mu naught, we got the mu r is the mu relative permeability. So that's basic way how we conduct the calculation. Okay. Very straightforward. If you design any inductor or transformer, we usually have to go through this calculation by hand or by your Excel, by your computer to do the design calculation. That's a really basic equation, how we actually design an inductor or transformer. So next topic will be sinusoidal excitation, right? Sine wave excitation also quite special. And in this lecture, I only show you sine wave. If a sine wave apply for a transformer, what happened? But you can see in other more complicated technology, they may think about do triangular wave or square wave apply to a transformer, what will happen? So firstly, then we can use this basic equation from Faraday's law. Voltage equal to the phi dt. Of course, it is the proportional number of turns. Then we can therefore rewrite the equation become this way. So now then we apply voltage in here. So we assume the voltage waveform are equal to this one. Assume voltage. And when we integrate it, then we can obtain become this format. So now then is the amplitude sine divided by n omega. So this is the peak amplitude, right? So we root 2 times RMS value, and then we can omega, which convert to 2 pi f n. So that means you can see that the peak magnetic flux will therefore equal this component, and then we replace this 2 by 4.44. So now then you can see this really famous formula. Many textbooks, many design will use this formula. That means RMS voltage are equal to 4.44 Fn5. That's the peak value. This is RMS value. So this really famous formula you can see in many textbooks. Probably in your undergraduate, you learn this formulation. And somehow people like to use the B field, so it's putting area here, then the formula B become this. So this is how this formula obtained. Okay. Any question? Just a quick revision of what you have learned before. Now let's look at a quick example. Also, a transformer, we connect to a sine wave, 60 Hz, 120. The plant size transformer is 100 turn. Calculate the B field, the magnetic field in the core, and also what's the current equation, how the current look like. When you apply for voltage, what kind of current appear in the transformer? And then given that the cross-section area of the core is 80 cm and the mu r is 2500, the length of core is 20 centimeter. So that we can just using the basic equation, this one, and then this is 4.44 FNB. So we just put all the component here, 120 volt RMS. You see this formula, the voltage equal to RMS, the B field or the flux equal to peak. So that's it. So do remember how we use the component. And then we just using the formula, we can work out the B equal to 0.56 Tesla. So although this equation is simple, but this is not application. When we design any transformer or inductor, then we know what kind of voltage we're going to apply for that component. Then work out the B field. So you need to make sure that B field will not cross the component to saturate, including if you design transformer, machine, motor. There's a limitation for the saturation for all the magnetic material, including, for instance, when you design a motor, so all the motor or FM material, this will be the saturation. We tend not to approach to here because the B field here are getting too high, will saturate. So we usually working on this region for different material. So that means if you using my equation to calculate B field to see you would approach to the saturation region, try to avoid it, try to work on this region. So every time when I calculate B field, if it's too high, then we just change the design to make the B field lower. Okay. So that's how we do that in normal design. So if you find that in your design, you find the B field is too large for your component, what you need to do is to increase number of turns. And here.
How much it should be normally?
Depends on material. For instance, you say in here, that's a silicon iron will be, say, 1.2 will be saturated. So you don't go beyond 1.2. Maybe don't go even 1.1. But for ferrite, will be about 0.3. Ferrite 0.3. The powder iron core will be 0.7. So all material are slightly different. So you better to check the manufacturer data, check the BH curve to see which part approach to the saturation. For me, I will tell all my students to say, if ferrite, then 0.3 is the maximum. And then for this kind of silicon iron, then that will be, say, 1.1 will be the maximum. Don't go beyond that. Otherwise, if the component approach to saturation, you have difficulty to control. You get really hot, higher losses. So we don't like that. And the permeability will get low. You see, the permeability here will be quite high, right? When you approach to here, the permeability getting much lower. So that means in theory, you use that design for your inductance, but when you operate it such a high current, you got less inductance. So you spoil your design. So that's the equation. This equation is simple, but give us a hint how we design the inductor transformer. So we use the control parameter n to do that. Or if you find that you don't have sufficient room to put your winding, you need to adjust area. Maybe you go to find a bigger core. If you find a bigger magnetic core, the cross-sectional area will be larger, then the B field will become lower. That's how we design an inductor. For example, see how you're now designing the tap inductor. Then when you design inductor, you use this kind of equation to look into limit the B field will not go beyond the component parameter. So this is a really famous equation, but really useful. I use it to design all my inductor transform really often. Anyway, so next thinking what is equation for the current? Then we firstly calculate the H field, because H field related current. So the B field 0.6, and know that this is a peak value. Divide by the mu naught mu r become our current. So the H field here is M per meter. And then we multiply. So this is our H field. So we divide by the number of turns, and then also and then the core length, if it's 20, and multiply by the core length, then will give us the H field. So here should be H times L divided by L. I got typo here.
Yeah.
That should be H, right? So that now give us the current requirement. So this current requirement here, then just driving current. You're going to see this current in the coil, in the winding. Of course, there's still a sine wave, so the equation will be, again, this is a peak value. When we using the H here, it's this H, peak, this current also peak parameter. So this will give you this formulation for the current. You're going to still see a sine wave of current. So these two, the H field and the I will be the same frequency, same phase angle in such a way. All right. So if you do some experiment, you can see how it look like. So if you do have time, you can conduct some simple tests, apply voltage there to see how much current you can get, and then to see if the current will be look like this. So this current is the current appear in here, right? You put a coil here, you can measure this current. This current also equal to sine wave, also equal to similar to the voltage frequency and the phase angle are related in such a way. So formula is simple, but give you a lot of the phenomenon, how we understand voltage, current, flux, and magnetic flux density. So next thing will be also really simple. I build turns ratio. We go to revise this thing so they understand the basic concept. So firstly, we all know that voltage conversion ratio equal to turns ratio. We all know that, right? We learned it. But how the formula come from? Probably in the high school, you have learned that. Let's have a quick look about voltage. So usually for ideal transformer, we assume all the winding resistance or the leak gauge is not being considered. I assume this is a more ideal transformer. Then the voltage conversion ratio will be valid. So that's to say, the basic Faraday's law, input voltage. So we assume this is input voltage, but the winding voltage we call E1. So I assume that all the resistance here disappears. So V1 equal to E1 anyway. So the induced voltage equal to defined dt times N. So secondary side is the same, right? But the flow component phi must be equal anyway, because flow through two of them. So that's why we can put these two together, become this equation. Really famous equation, everybody know. And then this turns ratio we call the N. transformer turns ratio. You see turns ratio here, the turn here is a plural S because we're talking about two kind of coil ratio, not turn ratio, but it's turns ratio. So by the conservation of energy, I think you also learned this formulation. Then the current ratio is equal to also turn ratio, but inverted because you can easily work out due to the energy or power conservation, right? So these two formulas are really famous. We have been using it all the time. So example. So for ideal transformer, connect the resistor 10 ohm, the turn ratio equal to 2. And then we can therefore.
How is it inversely put? How?
Huh? Sorry?
Why it's like opposite? I1 over I2 is equal to N2 over N2.
Yeah, I show you. Let me get a pen. Okay.
Well, in normal thing, we say V equal to IR. So V and I are like directly proportional in normal thing. Here,
for instance, equal to N, put on here. And then V1, I1 equal to V2, I2.
yes.
Yeah, power. So that's why the V1 over V2 equal to I2 over I.
Oh.
So equal to N. Yeah. So that's how we get to the, of course, you can see that the current ratio equal to the same ratio, mainly because of the power conservation. If the power, we got high power losses, that may not be the case. Right? So now then we can get to the formulation here. So if this ratio equal to 2, then we can see that this is equal to 2, then 120 input V2, and then calculate that will be equal to 60, right? So very strict, everybody knows, it's very simple, it's only high school stuff. And then output power will be V squared over R. V is equal to 60 divided by 10 ohm is the output, then we got 360 watt. Output current will be V equal to resistance equal to 6 amp. Input current, we can using this ratio relationship, we can get to 3 amp. Yeah. So very simple, straightforward, no ambiguous. And the next thing will be about the dot rotation. Have you learned about the dot rotation for transformer? Tell me how you understand. You can see that when you see any transformer circuitry, there's a dot rotation here. How do you understand that?
It's a direction of
Directional current, yeah.
Current.
Yeah, it's directional current, but how? Tell me more about that. When you do the winding in here, how do you know which one has the dot, which one without the dot? How to locate the dot?
Starting point of
the direction.
Starting point of the winding.
winding.
For the dot side.
Firstly, starting point of the winding. If you both sides, if we have dot here, in the secondary side, when we put a dot, that means this is also the starting point of the winding. But you also need to make sure the flow component will be the same.
Yeah.
So that is to say, you've got a magnetic core here. You put the winding here. You put a dot here. That's the primary side, right?
Yeah.
So now then, if I also put the winding here for the secondary side, where is the dot?
Up.
Huh?
Up.
It is up here, same.
Okay, yeah.
Continuation.
So that's up. So that means we are putting them in the same, the flux will pass through the same kind of component, right?
Oh.
So that's why we put a dot here. So when you apply positive, negative here, this also will be positive, negative. That's how we can see the phenomenon.
So if the second coil in the other side,
Then you just
so
move it there.
because the direction of the flux is different, so we need to put the dot in the underside.
That's right, yeah. When you move, just like you move in here in such a way,
It
you can
automatically.
imagine how this move follow the magnetic flux flowing
Okay,
to move it.
I see.
Then the dot will be unchanged.
Come
When you
under.
move here, the dot will not be changed. You make sure the winding direction is unchanged when you move. Just like coil, you just move it across to the other side, that's all.
No.
Then you won't be anything. So you need to think about carefully when you have this something like that.
Yeah.
Something, and the mission is positive. Yeah, so that's a really basic concept about would that be which one is positive, which one is negative, so on. All right. So that's basic concept about that. But however, as I say in here, the dot rotation, how we define physically the winding direction where we start the winding, but we don't, for circuit point of view, we don't quite care about the direction where we start the winding. We only care about the polarity here. So this drawing here will in here also similar here. When we move this to the other side, we can also have the positive on one side, the other side. So, but we only care the dot rotation when we apply positive here, 0 degree, this also becomes 0, not 180. So that's the concept we like to. So in here, we say we only care about the polarity in the winding appear in the secondary side. So this symbol here, we don't need to tell our user about the winding direction. We don't need to say, oh, this is clockwise, this is anti-clockwise. We don't need to say something like that. We just put a dot here. We say, when we apply positive signal in here, this side will become positive. We won't reverse the phase. So that's the key thing we need to say that. So when you see a transformer dot here, we don't need to know the winding direction, but we only to know these two will be in phase. Okay, that's the only message you need to know. So that's how we define the dot rotation. The dot rotation is important because it tells us how to connect many transformers together, including, for example, like if you got two transformers like this, how are we going to connect them in series, in parallel? If you don't have a dot, we have problem. For instance, if we have a transformer like this, two transformers. Then if you want to connect them, we need to look at the dot rotation. For instance, then connect this and this can parallel. Parallel is quite okay without problem. Input side. Output side, then we cannot just parallel them because the voltage cannot be matched. Yeah, if you want to increase the output voltage, because dot here, we can therefore connect in series. Then this will adding this one. Because these are the same phase, so we can therefore add them together to therefore nearly double the voltage. Yeah. But if you don't know the dot here, when you connect them, we can cancel the voltage if they're anti-phase, right?
Yeah.
So that's why the dot rotation tells us how we put the transformer together. Do you get the point, right? So that's why we all the circuitry we need to have a dot rotation to tell you how to wire, how to connect the transformer.
Therefore, the different polarity, we just don't connect them, right?
Yeah, that's true. You will see that if this circuitry like that, then these two cancel out, become 0. If this 1 to 1, 1 to 1, right? Then this will become 0. Yeah. But however, if like this, then the whole transformer here will become 1 to 2. Okay.
And it cannot be of the different polarity on the primary side, right? Because then it will also cancel out.
Of course, there's many configuration. There's some exam paper I'm going to ask you, right? It's not really simple, but it's quite a good way to solve it. Another connection here. Okay. So if you connect this in series, of course we can do that. Okay. So now then, but if we connect this in series, can we connect these two in parallel? Can we? Would there be any
Yes.
question?
If
Yes.
the voltage is the same, we can connect it parallel.
Yes, we can connect
Yes,
this.
okay.
We can connect this in parallel if you like. So now then we can connect this in parallel. Like that. Yeah, that's
2:1, right?
Yeah, and then if this 1-to-1 is 1-to-1, how about the total conversion?
How is 1:1?
Yeah. Now we are using two of these become one. Yeah, become
Yeah.
2-to-1. Yeah. So you see, just this kind of wiring connection for dot rotation has a lot of the phenomenon coming out. You're able to connect the transformer in parallel, series, parallel, you can produce 2-to-1, 1-to-2, 1-to-0.5, many things. The problem is quite simple, but you got a lot of the phenomenon coming out. So now that it's simple, only 2 transformers, but we can increase to 3, 4, 5 transformers. That could be quite useful. When you conduct the power conversion, you may need to look into different kind of the method to do this. So that's why, do remember something like that. So it's quite important for us to understand how to connect. And also, now you can see the important for the dot rotation. Without dot rotation, we are not quite sure how that can be. Something cancel out, something can be enhanced. Right? Any question up to this point? So here we just say, the circuit, when we see the dot appear on one side of the winding, this refers to the polarity is the same. They are the same polarity. That means no 180-degree inversion. So the dot rotation is important for us. How to connect the transformer in parallel, series, whatever. There's a lot of the thing in here. I think some professor may like to convert this one into some formulation. They got some special rotation formulation to show when we have multiple transformer connect in different way, how the result come out. Because the thing is, this thing, we need to avoid the circulating current. If you don't connect it properly, there will be some current circulate internally. And then this kind of connection can be extended to many other domains. For instance, you can have so we got a transformer in here, right? So this symbol is the magnetic core inside. So imagine if we have same, if I've got another core in here. So the phenomenon will also be changed, right? So he got 1-to-1, and then this, of course, 1 to another 1 in here. Then that's another phenomenon. They share the same core. So there's a lot of the interesting topic we can play around with them. So of course in here we connect this in parallel, then whole thing become 1-to-2, right? But however, if we have winding in here, can we connect these two in parallel? If this is a 1-to-1 in here. Yeah. The same share the same magnetic core.
Yeah, we did before.
Yeah. Then the thing about, can we connect them in?
Yes, if we connect in parallel, then you.
If you connect, if the final side, we can connect in parallel. Can we connect final side in series?
Yeah. I think, why not?
So that's why there's a lot of the interesting point here. Because they share the same magnetic core. There's something we need to ensure the number of turn ratio still can enforce, right? Another thing we need to look into a bit, the perfect ideal line transformer, that will straightforward. But the transformer never can be perfectly equal. If something get wrong, then there may be some circulating current circulating internally. They will get hotter and hotter. So that means although in all this we're talking about ideal transformer, but in case the transformer is close to equal transformer but slightly different, can we still connect in parallel series in such a way? So that's why we do need to consider. Just we assume that if they are practical transformer, not ideal transformer, we need to ensure that all this connection will be feasible. So this connection will be feasible if they're practical transformer. They're good because we now connect in series, even though they are practical transformer, we can still connect them in such a way. For this one, you can still connect in such a way, yeah, if they're practical transformer. But if some transformer is practical transformer, like this one, magnetic core, winding one, 4 winding here, what kind of way we can connect them? Because once you connect them, we cannot disturb their magnetic flux distribution. For perfect ideal transformer, of course, we can still connect them in series. Yeah. But however, if you want to connect them in parallel, then that's another thing we need to think carefully.
Isn't it the same, the different core?
Oh, the core, the same magnetic core.
Oh.
This is different core, two separate transformer. But how here is the same magnetic core, putting a number winding there. So this symbol means the magnetic core inside. So for definition, then we can see that this is more look like kind of the iron core, solid bar. But we do have something bar like this. Yeah. That's also something you may see somewhere. So probably that the dot one more look like powder, like the powder iron is dotted. Yeah. There's many different kind of definition. Yeah. But anyway, there's also just transformer itself will be another interesting topic, how we put them together, parallel series. The reason we do this will be trying to double the power, double the voltage, decrease the voltage. So when we don't have limited transformer, then we need to use this method. Another thinking will be single phase to 3-phase transformer. If we have 3 single phase, can you connect them into 3-phase transformer? There's also some phenomenon you need to look into. Yeah. In many cases, 3-phase transformer construction will be using a single core 3-phase transformer. But now then, if you are using 3 separate single phase transformer, can you connect in a way for the 3-phase transformer? So that's also something you need to look into. So anyway, you think about that, and then we may have some assignment to look into this area.
This transformer uses just one.
3 single phase to construct one 3-phase transformer. You see the symbol for 3-phase transformer could be like that, right? How that look like? And then what do you know the 3-phase transformer, how the winding look like, what the magnetic core inside look like? And then now then we have 3 single-phase transformer. How do we use 3 single-phase transformer construct this 3-phase transformer? Can we do that? Or we cannot? Do you know how a 3-phase transformer look like? What the magnetic core inside look like? Okay, go to the website to search up. Okay, that's an interesting topic. So I just in here just tell you about this transformer. When we revisit the transformer, we can see many things we are missing. We're not quite sure. Although it's a very simple topic, we learn in high school, maybe undergraduate, but when we visit them, there's so many things we are just not quite sure. But you are electrical engineer, you need to know that. Okay.
I did my undergraduate thesis on 3-phase transform.
Okay, you must be expert. Yeah. Okay, tell me. Come to here. Can you sketch the magnetic core for 3-phase transformer? How does it look like? Yeah. So share with your experience.
We have 2 types. So for 3-phase, we'll have 3 legs.
I think it's not very good for me.
So this is 1 leg, this is 2 leg, this is leg 3.
Okay.
So it can be winded like in 2 types. One is up and down, and another one is if we look the transformer from the top, one is inside and another one is outside, the primary and the secondary. So I use this one for my application.
Okay, tell me, now you got the free leg in here, right? And then why the free leg can be run in such a way? Would there be any automatic thrust inside? Would there be any crashing or any unbalance for magnetic thrust?
Like this? Yes, there will be a lot of losses in there because the upper and the lower coils are separate, so there will be a lot of losses. But if we use like this, the losses will be.
My question is, the magnetic, when we energize sideways here, we obtain the also sinusoidal thrust in this leg and also this leg and this leg. How can the thrust become mixed together without any disturbance by other phases?
Can change the polarity.
I mean, the magnetic flux are determined by the driving force, by the input current or input voltage, right? And then how the three phase flux appear in here, how they mix together. Would there be any flux that at the phase issue create the circulating current here? Of course, it won't, but why it won't create any circulating current or circulating flux in the transformer core?
Yes, it will create some eddy current. So
eddy current must, but would there be any circulating flux which we cannot make use of that?
No, sir.
But if we change the direction of the turn, then we can.
No. You see, we got three in here. One, assume this bit. So this 0 degree, this flux will be 120, this is minus 120, right? So when they mix together, they automatically cancel out. So we don't have any issue for the flux circulating because this are arranged in such a way, right? All right. So that's one way we make the transformer. So for this, there's many different designs. Some transformer may also have different shape. I can see some transformer, they use this shape. Even though using this, so winding here, and also winding here, they even put a star shape. So there's quite a lot of design for the transformer. So this one, then the magnetic link here compared to the middle one are slightly different. So slightly not quite symmetrical, but this is a very common shape. So that's why some people, they may like to star shape in here. So they all share the equal link for each branch. So there's many different kind of the design. So you just search up to see how we design the transformer. That also become a quite interesting topic. Even though for power electronic CTOL, we also design transformer, single phase, three-phase transformer, using this kind of magnetic topology. We have different topology to design the magnetic core to do the job. Anyway. So another terminology we need to understand will be the particle transformer. There will be some leakage component. So leakage component, I think we all know that there's a T model about all the components. So where this come from? Because when we have winding here, we assume all the magnetic flux will go to the core, and this flux will go to the secondary side, and the energize them will be induce the voltage on the secondary side. But however, there will be some small amount of flux. It's not linking the main core. It's just circulating in here. Or this amount is not that much, especially when the μR for the core is really large. But even though these are few thousand, we still have some leakage. So this leakage flux phi LIL for leakage, L1, this is L2 for the secondary side. So this flux linkage for the divided per unit current will become our leakage inductance. You see, our inductance definition is the flux linkage divided by the input current, right? So that's why that's a flux linkage for the leakage part in here. Also this one. So we can use this formulation. We calculate the leakage inductance. That's all. So once we calculate, then we can therefore write down This component is the leakage component for the primary side, this component for the secondary side. For the winding resistance, copper, there will be winding resistance, which is R1, and also R2 for the primary side, secondary side. We all know about that. And then, however, for the transformer itself, we do have another component called the core loss component, which although we cannot represent simply by the leakage component, but this component, when we apply any voltage to the transformer, we do excite the magnetic core. So that means you can see that the main winding, the main core winding here will be our magnetizing inductance. So the magnetizing inductance here will represent by two components. One is R, one is X. So this component mainly about the magnetizing inductance, the main coil, just like this coil here. And then another component is RC1 is the core loss, the loss component, because this core loss component mainly be due to all the thermal losses, hysteresis losses, the magnetizing losses, or eddy current loss all lumped together into here. So that's why this cannot be calculated anyway. It all depends on the design, depend on the material. But the magnetizing, this one, XML here, can be estimated quite well by using the basic inductor equation. So if you do any winding here, you can actually calculate the magnetizing inductor here, just using conventional equation for inductor. They will really much close to each other. So this model is quite common. We have transformer in here. We use ideal transformer in here. Either side have the leakage component and magnetizing inductance. Of course, I think you all know that we can therefore move the transformer from for the one end or the other end, and then refer this material into the primary side, easier for our calculation. So that is to say, when we refer the secondary side voltage to the primary side, so this voltage, after we refer them, we use to put a dash. So there will be a relationship between of the turns ratio and here, when we refer to primary side. And then for the current as well, will be inversely proportional to that. And then for the inductance, when we refer to the primary side, they have an n-squared relationship. So this relationship, I think, is well-known relationship for all the inductance, for all the reactance. So that's how we can use this model. Sometimes we call it T model to represent the equivalent circuitry. But anyway, so once we got this circuitry, then we can gradually to move on to do other tests, like the load test, open circuit test, and also short circuit test to get the parameter. I think you all know about this. But anyway, we'll stop here, then we'll continue next week. Okay. So those are the things about this topology. It's also an interesting topic for transformer, especially for future, when we study more about high frequency magnetic, we'll make use of them to examine the connection. Anyway, okay, thank you then. See you.